Okay. I'm going to add a couple of things here that I think you guys should know. So we're going to start with electromagnetic magnetic radiation. So often when we talk about electromagnetic radiation, most people saying, what the hell is this, right? So you guys kind of heard of it. It's those gamma rays, it's those X-rays, it's that UV light and visible light. You guys know visible light, the white light, is actually a whole bunch of colored lights that are put together, and all together they make up white light. And we can diffract those so that we can get the individual colors. And so that, I'm going to show you a little bit of that. One of my favorite labs is the spectroscopy lab. And, you know, because you get to see beautiful light, you get to see things catch on fire and change colors and stuff like that. So it's one of the best labs. So you guys did the flame test already?
Mm-hmm.
Yes?
Yes.
Okay,
The
good.
what?
Flame test. So it's one of the labs. It's the simulation that you should have done, lab number 2, I believe.
Mm-hmm.
Yeah, so you want to make sure if you haven't done it, you want to do it. And it's really late at this point, but that's all right.
Wait, what? I'm lost. I don't even know what that is.
You didn't do lab 2?
I don't think
Lab
so.
2.
Lab 2.
I thought I did.
Yeah, it would have been in lab 2, the simulation. You should have paid your kid to do it, or your brother, you know?
Oh, is that the one where you walk into that lab and you have to go get a coat and all that stuff?
Yeah, and
Yeah.
then, yeah.
Yeah. Yeah, I did it.
I thought that was for anatomy. I don't remember.
It all blends together.
It really does.
I can see her now. She probably just hits it and hits play and then go on and then come back and hits play a little bit later.
Something like that.
So energy is basically, it's transmitted at the speed of light, right? So almost all energy is transmitted at the speed of light. So the light, speed of light is 3.00 times 10 to the 8th meters per second. And this is what it is in miles per hour. But, you know, we're trying to get you guys to, you know, the metric system. So trying to convert you to the dark side. Okay, one thing that you need to know is that energy kind of has wave properties, or light itself actually has wave properties. And it has wave particle properties, it's dual properties. And so that's going to be kind of important for us to understand. And it's going to be important for understanding a little bit about the atom itself. Okay, so here, C equals lambda times nu. This, I know it looks like a V, but it's really a nu, as in I wear new shoes, nu. But it's spelled N-U, okay? So nu represents the frequency, lambda represents the wavelength, and C represents the speed of light. Now, if you think about it, when you guys are driving your car, right, and you look at the speedometer, what is the units for the speedometer?
Miles per hour.
Miles per hour, right? So miles per hour is considered to be your velocity. So the units for velocity is also V equals, this is not volume, this is velocity in this case. So that's why I say sometimes we use the same thing over. So I'll say V equals distance over time. And we use little t for time, d for distance, little d for distance. Okay? So if you look at this, and then I'll show you mathematically here in a second, wavelength and frequency are inversely proportional. So what does that mean? Inversely proportional. So speed of light is a constant. It's always going to be exactly the same. 3.00 times 10 to the 8th meters per second, always. Okay, never going to change. Okay, so if I have a large wavelength, what would I expect my frequency to be, large or small?
Large.
Are you sure?
Oh,
No.
Now, again, I'm saying, let's use a fake situation, right? Fake situation. So rather than putting this big number here, let's just say C is going to be 1. Okay, and here lambda is going to equal 5. Okay, so if lambda equals 5, what must nu be?
You're eating your chicken. I ate more. Oh, eat more. I'm not playing with you. No, that's your dinner. I'm trying to do my schoolwork. Sit there and eat.
is it my
Okay, Lucas.
1/5?
1/5, right? So nu is going to equal 1/5. Okay, so if lambda is 10, what would we expect it to be?
1/10.
1/10. Okay, which one is bigger, 1/5 or 1/10?
1/5.
Okay.
Okay, so if that's the case, then is nu increasing as lambda is increasing? Because I went from 5 to 10 for lambda.
It's decreasing.
It's decreasing. So they're inversely proportional. Anytime you hear the word inversely proportional, no, it basically means if one of them gets higher, the other one has to get lower. Okay? Simple?
Mhm.
If I tell you something is directly proportional, that means that they go up together, right? So if one gets higher, the other one gets higher. That would be directly proportional. So here we have, remember we're basing everything on energy. Energy is going to be equal to H over nu. Now H is also a constant. This guy is called Planck's constant. Oops. I should probably type that. Towards the end of the day, I look like I've been drinking, and I haven't really, not yet. I usually wait till after.
Hold on. What did you say about drinking?
Okay, so, and Planck's constant, I will give you the units, but it's not going to be pertinent for what you guys are doing. I don't want you guys to worry so much about it, but I want you to know how energy is related to it. So in this case, energy is directly proportional to nu. So if nu goes up, energy goes up, right? So nu being the frequency. So you guys are going to ask me, okay, so you tell me about this damn frequency stuff. What in the hell is frequency? Are you asking me that yet? Come on, Ro. I'm expecting it. Where is it?
Yeah, I'm lost.
Excellent. That's what I
I'll
wanted
definitely
to
learn
hear.
that.
Perfect. Okay,
What
so
does
let's
the
put
equation
this in.
say?
What was that?
The equation, what does it say? E equals what?
H times nu.
Oh, times. Okay.
Yep. So that's H nu.
And then nu is, oh, the V looking thing.
Yep. That's a nu. Yep. I know all these equations.
What V looking thing?
This here,
Where?
this right here, this is really like this. That's nu. So this is lambda times nu,
Oh.
even though it looks like a V.
Oh, okay.
That's the same thing as it is here. But this is H, and that's Planck's constant. And I'm pretty sure I misspelled Planck. I'll look it up just to be sure. I'm not an English major. You'll notice that. I'm definitely a scientist. Although that's no excuse.
So the H is the Planck's whatever.
Planck's constant. So I'll say that. Type it in here so you guys see it. Seeing is believing, right?
Sometimes.
okay? And so you can actually calculate the frequency. I mean, you can actually calculate the frequency from energy, or you can calculate the energy from a frequency. So light is at different frequencies. Different color light is at different frequencies. I'm going to show you that here in a second. Now, I'm blowing your mind. I know I'm blowing your mind. Okay, you guys are ready? Okay, next slide is incredible. Best slide ever. Why? Because it has so many colors, that's why. I knew you were going to ask me. Okay, so here, this is the wavelength. Wavelength is measured by peak to peak. And the wavelength is just the distance from peak to peak or trough to trough, right? And that's going to be your wavelength. So these are all of the different wavelengths. So different energy particles have different wavelengths associated with them. So for instance, gamma rays. Gamma rays are basically from 10 to the minus 16th lambda all the way to 10 to the, I guess it's about 11, almost 11 lambda. So that's going to be your gamma rays. And then you get into X-rays, and then you get into UV light, then you get into visible light, then you get into infrared, then we get into microwaves, then we get into radio waves, and then we get into those long, long radio waves. Okay? So if you look here, the wavelength is increasing, right? So the distance between peak to peak is increasing. As the wavelength is increasing, if you look up here, the frequency is doing what?
Decreasing.
Is it increasing or decreasing?
Decreasing.
Decreasing. Okay? Man, didn't I just tell you that? It's incredible when equations actually work in real life too, right? It's beautiful. To kind of give you an idea of the wavelength, right? So an atom, the size of an atom is about anywhere from 10 to the minus 10 to 10 to the minus 9, right? So depending on our atom. So it's pretty damn small. A virus, 10 to the minus 8. A bacterial cell, 10 to the minus 6, and these are meters, right? An animal cell, that's about 10 to the minus 5. The thickness of a CD is about 10 to the minus 3. The width of a CD, so that's about 10 to the minus 1. I think that's a little small, but you know. And then your dog. Your dog is about 10 meters, right? So kind of give you perspective. And then it also gives you perspective in terms of how big those waves are. You guys see that?
Yes.
Okay. So it don't mean nothing unless we can do equations, right? So if blue light, so this here is all white light together, right? So we mix it together, it's all white light. But we can actually take it so that we can get each light, each color discriminately, right? So we can get discriminate lines of light. So blue light is about 400 nanometers, right? So if using our equation, C equals lambda times nu. Okay, C equals lambda times nu. Now, if I tell you that lambda is equal to 400 nanometers, can you tell me the frequency? And by the way, I forgot to mention this, but frequency, nu, is the units for nu is 1 over seconds, or we'll often call it a hertz. Being over time hurts a lot. So hertz. Okay, so can we calculate nu? So what is the speed of light? C, is it the speed of light? What is the speed of light?
3.00
3.00 times 10 to the something.
Okay, so C equals, and that's meters per second. Okay, so can we solve for nu?
Yes.
Okay, so how will we do that?
Like unit conversion.
3.
I always like to put my equation in the answer that I'm looking for, right? So I have nu equals to C over lambda, right? So my first question is, meters, nanometers, are those the same units?
No.
Okay, so one of the first things I would want to do, since I'm a good student and knowing what I know, I would probably want to try to make sure I have everything in the same type of units. So I would probably, on the side, making it easier for myself, change my nanometers to meters. I don't know, that's what I would do. How do you guys feel about that?
Mhm.
Okay, so you guys need a little bit of coffee too, huh?
Let's do it.
Let's do it. Okay, Jamie,
Yes.
I'm gonna use those skills. So you guys ready to share those skills with me? So I have 400 nanometers. How many nanometers equal a meter? Do you want me to tell you how I always remember?
Oh.
Nano, nano 9, nano 9. So I know it's 10 to the 9th power. So 10 to the 9th nanometers equal a meter. They both start with N, 9 nanometers. That's how I remember it.
Okay. That's a good way of.
Don't work for everything, but at least it works for that one.
Mhm.
Okay, so if I did this, what are you guys gonna get? Put in scientific notation. And let's assume that it's point. I gotta fix that in my problem. I keep doing that. Oh, did I say my problem? That would imply that it's gonna be on the test or something like that. So how many sig figs am I expecting?
One. One sig fig?
So what did I say about equivalencies?
Oh, no, hold on. It's gonna be.
They don't count as sig figs.
They don't count as sig figs, and I put that decimal there so that I would have how many? Oops.
1.
Is it gonna be 1?
1.
I put the decimal right after that 0
3.
so that I would have how many?
Oh, 3.
How
1.
many? 1?
3.
Oh, 3. So times 10 to the what?
-7?
That is correct.
Oh, okay.
So since we know that this is 400, that's like saying 4 times 10 to the negative, 4 times 10 to the 2. And then we're dividing it by 10 to the 9th. So that means that this becomes a negative since it's gonna be flipped up top. So 2 minus 9 is gonna be -7 for our exponent. So a quick way of doing it. Okay, so now we got it in meters. So we can plug it into this beautiful equation that we wrote up here. My beautiful handwriting that Ro is gonna mess with me about all day. So we plug in speed of light. and that's meters per second. And we divide it by 4.00 times 10 to the negative 7.
-9. Oh, 7. I'm just kidding.
And that's meters. My meters are going to cancel out. And then I'm going to be left with 7.50 times 10 15. Or no, sorry, to the 14.
Yeah. Oh, no, never mind. Never mind. Because I forgot we have 3 sig figs, so that's the reason why we have the 0, right?
That's right.
Okay. So disregard that.
Okay, 1 over seconds, or I could say just 7.50 times 10 to the 14 hertz. Hurts so good.
So we can use seconds or hertz.
You can use 1 over seconds. So you see it's 1 over seconds.
Okay.
That's equal to a hertz.
Okay.
Okay, so frequency basically is the number of cycles. So cycles doesn't have a necessarily unit, even though we say cycles, right? So it's the number of cycles over a given point of time. Okay, so like we go through an area, how many cycles are going through that at a particular point of time? So that is frequency. Okay,
I'm sorry, you said the number of cycles per what?
per time.
Per time.
Yep.
Okay.
Is that a capital H and a lowercase z?
That is correct. That is a capital H and a lowercase z. It stands for hertz. The way we spell it, hertz, because you'll see it probably on the exam. Hertz. Kind of like the rental car.
That would be good.
Okay, piece of cake?
Can we do another one?
Of course. We can do another one, right? Okay. So let's see if what we will change. Okay, let's say we're talking about green light. So, and we're going to assume, we're going to say like lime green light. So we're going to say 550. Oops. So lambda is going to be 550. We know the speed of light isn't going to change. So what are we going to do?
We're going to convert it to meters.
We're going to convert it to meters.
Mm-hmm.
I have a quick question. So the speed of light is always going to be the 300 times 10 to the 8 meters?
That is correct.
Okay.
Because speed of light is what?
It's a 300?
I know, is it 300 or?
It's not 300, it's 3.00. Sorry.
Oh, okay. Sorry. Gotta ask.
I'm sorry. It wasn't Ro who's messing with my writing. It has to be Eileen. They're taking turns. They're picking on me. Okay, so we have 550. Then we know that 1 meter has how many nanometers?
9.
10 to the 9. Don't forget that 10 part. That's important, right? 10 to the 9th power. Okay, so then here, that's going to cancel out my nanometers, and then I'm going to be left with just my meters, right? So then this should be
5.50 times 10 to the negative 7.
that is correct.
Yes.
Wait, where do we get the -7 from?
Because if we have 7, I mean, if we have 9 underneath the bottom,
Mhm.
that means it's being divided by. So that means that when you come up here, this is like 5.50 times 10 to the 2, right? Because that's what 100 is. 100 is 10 times 10, right?
Mhm.
Okay, so then I have 10 to the, since it's at the bottom here, we can also call it just times 10 to the 9th. Sorry, not the 9th, the negative 9th, because at first it's on the bottom, so we're bringing it up. So if we have 2, 10 to the 2, and 10 to the 9th, you can just add those exponents together. So then you just get 10 to the -7. So anytime that you have your base is the same, you can add up the exponents, because 2 minus 9 is -7. Is that correct?
Yes.
Okay, and that's meters. Okay, so then we can plug this into our equation up here, where we have nu equals c over lambda. Okay, so here I have 10 to the -7, and I have 10 to the -8, right? So that's going to be 10 to the what? If I was just looking at that. We're going to ignore this for a second. We'll get back to it.
So I divided everything and I got 5.45
Okay,
times 10 to the 14th.
that is correct.
Yes. Okay. Cool. Oh, and I have a question, Dr. Henry. So what do we always use nanometers, or can we use other units? Are there is other units also used for this?
Well, you tell me. You can use nanometers. Nanometers work down here because that's what they're giving to us. But if we're looking at, let's say we are looking at microwaves, right?
Mhm.
So the units here are meters. So that's 10 to the, we'll say 10 to the minus 1,
Okay.
right?
Yes.
Or if we were looking at radio waves, right? So that's 10 to the 1. So that's 10. So we use meters in that case. So it just depends on what you're being asked,
Oh, okay.
right?
Mhm.
So like we're doing like a new equation and you took off the 4.00. Why didn't you take off the equation from the top?
What do you mean? I don't understand.
The 3.00 times 10 to the power of 8 meters per second.
What do you mean by why don't I take from there?
Like why is that there still, like, and you just changed the
Oh, because I
bottom
was being
part?
lazy, because we know that c, the speed of light, is always going to be exactly the same. So why would I erase it when it's going to be exactly the same?
So that's like the equation for C.
Yeah, so c equals lambda over nu, that equation, and then we just change the equation so that we can solve for nu. But we know that c means the speed of light. Speed of light is always this value right here, 3.0 times 10 to the 8th. Always, it never changes.
Okay.
So light always travels at the same speed. That's the reason why, you know, we are able to get light the way we get it, you know?
Mm-hmm.
Because it travels at the same speed.
Okay.
Okay?
Yeah.
Piece of cake?
Yes.
Okay. So the important part is you're talking about distance, right? And you're talking about frequency, right? And velocity, right? So just pay attention to units, make sure everything cancels out, you'll be okay. Piece of cake?
Kind of.
Kind of. Well, make sure you get it. If you don't get it, talk to the tutor, because it's definitely going to be on the exam. That's a promise. Okay, so as you saw, all of those lights, all of the different colors and white lights, that's called a continuous spectrum, right? So this here, continuous spectrum. So we have cases where we have continuous spectrums, but if we play with a single atom and we excite the electrons in that single atom, those guys will give us a discrete spectrum or a line spectrum, right? So literally it would be one color, you know, another color and another color, but it won't be all of the colors, okay? Because the electrons can only be excited to certain energy levels. And then once they're excited, they're gonna release that energy, and that's the light color that you're gonna see, how much energy is being released, okay? I'll show you an example here in a second. It gets pretty cool. Excuse me. Okay, so every element is unique, so they're not going to have the same spectrum because they all have different electrons. Okay, different number of electrons. Okay, you guys get that? Do you agree? Do every element have different number of electrons?
Yes.
Yes.
So hydrogen has a different number of electrons than carbon.
Yes.
Okay, good. Glad you remembered that. Okay, so the energy that's being released from those electrons, right? They're considered to be massless packets of energy, and those are your photons. But they're not really massless because the electron has mass associated with it, but it's just so light that we make the assumption that it's massless, right? It's just really light. Okay, so the thing that you need to know is that light has what we call a wave-particle duality. It acts like a wave and it acts like a particle, right? So it moves in a direction. It has vector associated with it. But it also has that wave function going on, so it oscillates, okay? So light is really oscillating. Okay, so this is what a wave looks like. This here represents our wavelength. So you see the wavelength. And then here, this can help us measure the frequency. So we have 2 peaks before we get to there. Here we have 4 peaks. So this one has a higher frequency than this one, since it only has 2 peaks compared to the 4 peaks. But this one has a bigger wavelength, right? So the bottom one has a higher frequency. The top one has a lower frequency. The top one has a bigger wavelength. The bottom one has a smaller wavelength. Okay? Piece of cake?
Yeah.
Okay, so here, this is just showing you that the light can be reflected, through slits of beams, and then a prism will actually show us the different colors of that spectrum. So, have you guys seen a rainbow in the sky after it rains?
Yeah.
So in that case, what's acting as our prism?
The water.
The water, yes. So water is acting as a prism so that we can get that whole spectrum. Okay? So here's an example where we have hydrogen. So we have hydrogen gas added in this tube, and we're exciting the electrons in hydrogen gas by adding this electricity. So we're putting in a whole bunch of electricity, and that one electron is being excited. But it's being excited in different energy levels. And we're going to talk about that in a little more detail. So as a result of it, and since we only are able to see visible light, so our eyes, we have trouble seeing UV light. Well, we can see UV light, sort of. But when we get to those lower ends of UV, ultraviolet, got to tell you that. Huh? Okay, UV light. So we have gamma rays, X-rays, UV. So here, this is blue. Violet is right on the other side, or purple. So UV, ultraviolet. Okay, so that kind of gives you its orientation. And then here is infrared. So if you look at it, it goes from a purple all the way over to the other side to a red. And this is infrared. We can't see infrared with our eyes, and we can only see certain that really close to the visible light spectrum of UV. Okay. Okay, so if we have different elements, they're going to have a different pattern in that visible light range. So this is hydrogen. This is what hydrogen looks like if we use a prism to diffract those energy levels. This is what mercury looks like. And this is what neon looks like. So are they the same?
No.
Okay, so they're clearly different, right? And they're different because they have different numbers of electrons, and those electrons are able to be excited differently. Okay? Okay, so there's this guy named Bohr. He came up with this theory, this model of the hydrogen atom. Now, this model worked really good for hydrogen, but it sucked for all of the others, and I'll tell you why here in a minute. But he was the one that kind of got us started and kind of thinking about this. And so what he said, basically atom consists in a dense nucleus, and then you have these electrons, these negatively charged electrons orbiting it, right? So they're in orbit around that, just like, you know, how the planets orbit the sun. So the nucleus is like the sun, and the electrons are like the different planets, okay? So, and if you think about how our solar system, is our solar system all densely packed or really, you know, packed together or anything like that? Or is there a lot of space between us and our next planet?
There's a
A
lot.
lot of space.
There's a lot of space. So he said, you know, these are just like the planets. There's this space between them, right? So there's a lot of empty space in there. And so that pretty much held up, okay? And then he said that, you know, all of the energy that is really involved in that particular atom, that's going to be, all of that is going to be due to electrons, right? So electrons are going to be the ones that can be excited, where the stuff in the middle, that stuff isn't going to be able to be excited because it's located in the middle, okay? Okay, and then so he just basically says that it's quantized. Quantized basically means that it has discrete possibilities, right? It's not continuous, right? So like we saw those 4 different colors for hydrogen, that shows that it's quantized, and you don't see that continuous spectrum that we see for visible light, okay? So this is just a little figure that basically shows us. So this is kind of like that continuous spectrum, you know, this ramp here, because it's a gradient, it just goes right into each other. Where what we really see in terms of quantum is like steps. Okay, you got this first energy level, then you got the next energy level, then you got the next energy level, then you got the next energy level, right? You see that?
Yes.
Okay. So, let me take a drink. This is basically Bohr's model of the hydrogen atom. So this here is the nucleus. And so this is considered N1 would be your first period, is your ground state. Now, Bohr says that I can excite this electron And when I excite this electron, it can jump up to the second energy level. If I put enough energy into it, that it can move to that energy level. It can jump up to this third energy level. It could jump up to the fourth energy level, right? So just depending on how much energy I put in, I can get it to excite to those different energy levels. Now, how many of you guys drink Red Bulls?
Mm-hmm.
Have you guys ever been out drinking and you have, what are they called? Cherry bombs, cherry vodka and Red Bull?
No,
No.
Jaeger bomb before.
Yeah, the Jaeger bomb, which is Jaeger and Red Bull.
It's a Jaeger, I think it's Jaeger and Monster.
Monster. Okay, same difference, some energy,
Oh, nasty.
right? So if you have a couple of those at, you know, right? When you're at the club, you're just like, yeah, yeah, oh yeah, right? But as soon as the club time starts to end, what happens?
Crash.
You crash and you crash hard. So the electrons do exactly the same thing. We put energy in them, they're like, oh yeah. So they jump up to that energy level. And then when they crash, they release all of that energy that was put in there. Okay? And that's what we see as light. Okay? And we often, when my instructor, he tried to explain this to us, he calls it the quantum jump or the quantum leap. And so basically what he's saying is that you can put enough energy in there to push that electron to that very next level, the one next to it, or you can just skip to like 6 levels and it don't matter if you have enough energy to do it, right? And you can pass through it without stepping through each of those energy levels. You won't see that electron go to each step, it just shoots straight up. So it's like magically appearing right at the 6th, right? So you don't have that transition or that passage to those other energy levels, okay? So that's considered the quantum leap. So if we think of it as cooking Thanksgiving turkey. So you stick the Thanksgiving turkey and then it magically appears on the table. That's what it kind of seems like. Because it's a whole nother levels. You don't see all of those steps in between. They're not measurable. You don't see them at all. Okay? So it's kind of like you stick it in the oven and it's on the table. Okay? So that's considered a quantum leap. There's a whole TV show based upon it. Google it, or I should say YouTube it. Okay, so ground state is the lowest possible energy, and the excited state is all of the energy that's being absorbed to shoot it up to a level that's above ground state. And then it's gonna crash, right? Because the excited electrons are unstable, so they're gonna have to release that energy. They can't maintain it. Okay, so those excited electrons are gonna fall back down. This is a picture just showing that. Okay, here we're at ground state. We pump in some energy, we shoot it up to this energy level, right? See, this is that energy being pumped into it. So it's up here, it's like, oh yeah, and then all of a sudden it crashes. And then it releases all of that energy, and all of that energy that's being released, that is the light we see. So if it's at a different energy level, that's gonna be a different color, right? So this is gonna give me one color. If we put enough energy to put it up here, that's gonna give me a different energy level. So remember when I said that whole thing with nu? So that energy is going to change when our frequency changes. So the different color is going to give us those different frequencies, right? So you can actually calculate it. Okay, so I gave you the groundwork, you know, the behind the scenes tour of everything. So now let's talk about what does it mean to you. Okay, so there are 4 quantum numbers that defines each electron in an atom. So those 4 quantum numbers are kind of like an address, right? So Ro lives, where do you live, Ro?
1935 North Kensington, Hanford, California.
Okay, so you guys know where to go when we, you know, so, okay. So Ro has a very unique address. Now, Elaine has a different address, right? Because Elaine is in Kalinga. She lives in a different place. They don't live together, right? We don't want to start rumors either, okay? Okay, so they're in two different locations. They have two unique addresses. They're never going to be the same addresses. So that's the same thing with each electron in an atom. Each electron in an atom has a unique address. It's made up of 4 components. One is called the principal energy level, or we refer to it as the period, right? So that is going to tell us where that electron is. It's giving us that location of that electron, okay? You guys see that so far?
Yes.
You want me to show you? Prove it to you? Because I know I see doubt in people's eyes. Veronica's saying he's full of crap. I don't know. It sounds like some magical BS going on here. If I can get out of this, if I can get out of my class, there we go. Let's see.
Watch a video.
Watch a video. Okay, so here are your periods, right? So each of these represents a different energy level, right? That's that first energy level. That's the second energy level. That's the third energy level. That's the fourth energy level. So we're telling you that each electron in an atom is located at a different point, okay? You guys get that? Okay. Now you guys got to wake up here soon. You're making me fall asleep.
Probably need a Jaeger bomb.
Yeah, we all need a Jaeger bomb. That's right. Okay, so now we have what we call sublevels. Sublevels, those are going to be blocks. So this is the S block. This here is the P block. This here is the D block. And this down here, right here, is the F block. So if you guys look at this here, these are space holders. So these guys are really in the D block. Okay, I'm going to repeat that because you're going to ask me in a second. These guys here are really in the D block. So the F block is between the S block and the D block, only in these last two, okay?
Wait, where's the D block?
This here is the D block, right here. This right here, from here to here, is the D block. So all of these guys are in the D block. And these two spots here, those are really these guys right here that are in the D block. These guys here, down here, that is your F block. F. I should probably put them in different colors, but that's all right. And we write it as little f, not big F, even though I'm, okay? So little s, little d, little p, okay? So those are your sublevels, okay? And then we have what we call orbitals. In every orbital, you can only have 2 electrons, okay? So there's 2 blocks here. So this block represents 1 electron. This block is going to represent the other electron, 2 electrons, right? So group 1 and group 2, that represents your 2 blocks. So S would have how many orbitals?
2.
Okay. It would have 2?
I would have 1.
It would have 1, right?
Yeah.
Okay, so P block has 1, 2, 3, 4, 5, 6. It can hold 6 electrons in the P block. How many orbitals can it have?
3.
How many?
3.
I heard somebody say 3. 3 is correct. Okay, this is for row. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons can be held in the D block. So then, or in the D sublevel. So how many orbitals are in the D sublevel?
I'm gonna say 5.
That is correct.
How did
Okay, let's see. So Stephanie, you got it? We have the F. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 electrons in the F orbital, in the F sublevel. How many orbitals are there? How many electrons can be in an orbital?
14?
So there's 14 electrons, right?
Yeah.
So we have 14 electrons. How many electrons can be in an orbital?
I'm not sure. I'm confused with all of this.
Okay, I will say it again. Every orbital now I want you to write this down. Okay, a orbital can only have 2 electrons. And we have 14 electrons in the in the F sublevel.
Oh, okay.
So then how many orbitals are in the F sublevel?
Uh,
7.
Question is, how many orbitals are in the F sublevel? So if we have 14 electrons and all together in the F sublevel, right, it can hold 14 electrons. How many orbitals are in the F sublevel?
7.
7, that's right. Okay, so I'll do a recap. Let's do this the right way. So we have 2 electrons in S. We have 6 electrons in P. We have 10 electrons in B, and we have 14 in F.
Electron.
So we have 1 orbital in S. We have how many in P?
3.
3 orbitals in P.
P? Yes.
We have how many in D?
5.
5. And we have how many in F?
7.
No, 7.
That's correct, 7. Okay, so if there was a G orbital, what would you expect it? If there was a G sublevel, how many orbitals would you expect it to have? Look at the patterns.
Oh, it would have
18.
9.
It would
Right?
have 9. That's right.
I'm getting confused. What?
Who says I'm getting confused? What?
Me.
Okay.
Oh, wait, you know what? I'm looking at the electrons, not the orbitals.
Okay.
Okay, never mind.
So,
I got it.
yes. So what happens is after you get to F, then we start going to G. So in theory, we can have as many atoms on a periodic table that exist. But the problem is that all of these here, we haven't found real ones. These are man-made. All of the ones up here that are in parentheses and stuff like that, those guys are man-made. So they're only stable for a little bit of time, and then they start breaking down, right? And so this here would be F. So there's the potential of having a G and an H and an I. So because our periodic table is gonna grow, right? At some point, once we figure out how to stabilize those other ones. So,
Dr. Henry, where's the G at?
it doesn't truly exist, but in theory, it can exist. So if you were a theoretical chemist or a theoretical physicist, right, you calculate all of this and you calculate that in theory, it really can exist. So I'm just asking you, if you look at the trend, pay attention to trends, right? So if you look at this, 1 orbital, 3 orbital, 5 orbital, 7 orbital, what would we expect H to have? So 9 would be, G would be 9,
Oh,
H would be what?
okay. I know it should be 11.
11.
That's right. Okay, you guys see that?
Yeah, got it.
Okay. Okay, Stephanie, are you with me now?
Yeah.
Okay.
Oh, my hands are flipping Spanish. So it's these two that are D. Yes. Okay. Yeah. Where are they? Oh, it's right here. Yeah.
Okay. Okay, the last thing for this course, what you guys need to know is how many, instead of how many there are in each orbital, we know that the max you can have is 2. We're just going to be worried about how many are in the subshells, right? Because we're not going to get into the nitty gritty. We're not going to need to know every little address because, you know, a chemist under the right conditions and with the right equipment can play with each electron in that atom differently.
I'm gonna close this door.
And that's not what we want to do. You guys just want to understand how it bonds, okay? Okay, so this is basically telling you everything that I talked to you about, right? So N, meaning the very first one, that's your periods. We've talked about the S, the P, the D, and the F sublevels. And this is just basically telling us our energy levels. Let me go back. Okay, so for instance, N being that first principal number, we have a 4S, we have a 4P, we have a 4D, we have a 4F. I'll show you this on the periodic table because it makes more sense with the periodic table than just doing it with on this blank piece of paper, right? So the thing that you want to know is, right? So let's use the periodic table and then we'll come back to this. Okay, so we're going to see how much you guys remember for what I'm talking. How much you remember for what I said earlier. So what block is this?
Block
S.
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 Okay, so this is our S block.
Mhm.
Okay, what block is this?
E.
P.
P.
E.
Okay, so I want to say one thing. Helium is really over here
In the S block.
in the S block,
Yeah.
okay? But that's just helium,
Okay.
okay? Now, what block is this?
E.
E.
D.
E.
D as in donkey?
Yes.
Yeah.
Okay.
Mm-hmm.
And then this guy is
F.
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 Okay, S, P, D, and F, okay?
S, P, D.
So we're gonna start with hydrogen because hydrogen is easy.
Those are D.
Then we're gonna go to helium, and then we're gonna make it a little harder, okay?
F, P, D, F, F.
Okay. Okay, so for hydrogen, if I wanted to write the electron configuration for hydrogen, since I know all my blocks, how many electrons does hydrogen have?
1.
1. Okay. So hydrogen is located here. So I would write, this is the period it is. So I'd write 1 S, and the number of electrons that would be in that 1s would be 1. Piece of cake? You guys see it?
Yes.
Okay, you guys have that look? You're starting to worry me a little bit. I see some sweating going on. Jamie's starting to do this a little bit, you know. So helium is also in the 1, right? It's located right here. So it has 1 S. And how many electrons does helium have?
2.
2.
2.
1s2.
Okay. So then we write helium as 1s2. Now it's a noble gas, right? So it's happy. It's stable. Okay. So let's go to boron. So I'm going to do this first one, and then hopefully you guys will see the trend, and then we'll see if you guys can work it out. So we start at the very beginning. Boron is located here, but we have to go through all of these steps. So we have what is up top here? That's 1. S2. We have the, in the 2 block, or in the 2 period, we have 2s, and there's 2 of them there, 2 electrons, and then we get to boron. Boron, there's only 1 in the p, so it would be 2p1.
I'm confused.
I've heard that. I'm confused. Okay, so it's kind of like a running tally, right? So it's kind of like these are cubbies, little boxes. So let's say I have, I'm looking for something. I have a cubby hole, right? And they're little boxes. Have you guys have you guys played Mancala?
Yes.
Yes. Anybody
the one
not
with the
played
beads?
Mancala? It's the one with the beads.
No.
Yes.
Yeah.
Okay, hold on.
I played it, but I don't know how
Talk
to
to yourselves, argue a little bit. Okay. You guys see my screen?
The game I want to talk about now is Mancala.
Okay.
Mancala is a
Yeah.
fun game. The goal is the cup and the one on this side. This is to start the game. You have 4 steps. The last stone that you
Okay.
play.
So
Turn is done. Now turn is done. Now it's this person's turn. And let's say they want to start here. Then they would put 1, 2. They put 1 in the Mancala bucket, and they put here.
okay, so we're not talking about necessarily the game Mancala, right? So what happens is that you take these little pebbles and you put them 1 by 1 by 1 in each of the different areas. So on your periodic table, it's like you have all your electrons in your hand, right?
Mm-hmm.
This guy is 1 spot. So how many electrons does boron have?
5.
Altogether, it has 5, right? So we put 1 in the 1s. We put a second one in the 1s. So that's why we get that 1s2, right? Because there's 2 electrons there. Then we put 1 in the 2s. And then we put another one in the 2s. That's how we get 2s2. And then we put 1 in the 2p, right? And so that's why we have 1 in the 2p. So if you add together, that's 1, that's 2 plus 2 plus 1, that equals what?
5.
And how many electrons does boron have?
5.
Okay.
Okay.
Kind of get it.
I'm kind of getting it, but I was never good at that game though. So
I never played that game.
That game itself looked confusing.
Yeah, I never got. I would just throw the pebbles in.
Okay, that's all right. You're gonna get it, and then you'll want to go play the game. Okay, so let's do SI.
Can you repeat it again?
I sure can, but we're gonna do it for SI.
All right.
Okay, so SI. First off, where's SI?
Action.
The 14.
It's 14 and
It-
where?
3,
P
14.
block.
Oh, and the P block.
Period 3. Group what?
P.
Right?
Period what?
3,
3.
Group 3. I mean period 3 and group what?
14.
14.
Okay, so I have it circled in red. Okay, how many electrons does it have?
14.
14.
14. Okay, so we always start at the very beginning. So we start here. So we're putting our very first electron in this spot. So that would be 1,
1s1.
1s1. But then we also have another one to put in here. So altogether, we're putting how many in the 1s spot?
Oh, 3.
How many can the s orbital hold?
Yeah.
2.
What did you say? Did you say 2?
Yes.
Yes.
1.
2 is correct. It can only hold 2, so we can't put 3 in there. Okay? So then we have to go to the next energy level, and that would be the 2. So then we put it's 2. And then the first and the next energy level is the S block. So how many can the S hold?
2.
2.
2.
Okay? And then we go over here. What is this block called?
P.
P block.
P.
So then we're it's still in the second period. So it's 2p. And how many? What is the maximum that can hold?
P. 3. Oh, 6.
6. Okay, then we get to the 3 period, the third period. So we're back at the S.
3s.
How many? 3s.
3
And what's the next it can hold?
2.
2. Oh, I get it now.
And then we go over here, and how many are in there? How many? We have 1, 2,
So
right?
3p2.
3p2.
3.
3, P, 2, 3, row 3, P block, and it's 2 right here.
My 2s are horrible.
Huh.
Okay, so that's how many? We have 2 plus 2 plus 6, that's 10, plus 2 plus 2, that's 14. Is that 14 electrons?
Yes.
Yes.
Okay.
I'm so excited, I get it. Am I the only one that gets it?
Yeah, I got lost.
I got
You
it.
got lost?
I'm gonna get this on the test
Pay
like right
attention.
now.
I'm gonna, see Jamie, you're wandering. Don't wander with me. You gotta pay attention to the details, okay? So now we're gonna do one that's hard, just because you got lost. Okay, we're gonna do chromium.
lost too, huh?
So this one's for Jamie, right?
Follow me, follow me. And then, so I'm gonna ask you, first off, how many electrons does chromium have?
24. 24.
It has 24, okay? Let's see. Trying to keep this, trying to be lazy because I'm gonna need it here in a second. It just does not want to work with me. Being difficult. Okay, Jamie. So you're gonna have to get this. This is you, all you. So we're working on chromium. So the first thing that you're gonna do, I'm putting you on the spot. That's the way you learn.
Okay.
You learn under pressure.
Don't get mad at me.
Oh, don't worry. I will a little bit, but I won't hold it against you. It only means I like you.
Okay. So let me write this down so I won't get confused.
Okay, Jamie. Okay, we always start at 1.
Okay.
Okay, so how many electrons how many, what do we have? We have 2 electrons that can only be held in the 1 level. Only 2 electrons. So we're starting with what sub-level?
We're gonna start with S.
S. And how many can an S orbital or an S sub-level hold?
2.
2. Okay, so then we've already done this one. Okay,
Okay.
we're just gonna cross them out as we do them.
Okay.
Okay, and then we go to 2, and then we start off. Where do we start off at?
2. We started. Wait. Yeah, 2, and it's gonna be S2.
Okay, S2. That's right. So that gets this guy.
All right.
Okay, and then we come over here, right? Because that's still on 2, so we want to put our 2. And then this guy is what block?
You're moving around a little bit too fast. Hold on.
Oh, I'm sorry. This right here.
That's 2.
It's
Okay,
2.
We're on P block. P block.
P block. Okay, so I'm going to put P. So it's 2P.
6.
And that's right. 6. That's 1,
Can I ask a
2,
question?
3, 4, 5, 6. Now don't do this on your periodic table that you have printed out at home.
No, I'm gonna get another one. Honestly, I'm
Where
just
can
gonna.
we get the 2 for that one? This is where I'm lost.
This is where you get lost?
No, this is,
Oh, I get it. Yeah, I get it.
where do we get the 2 for the 2p6? I know
Because it's at the level. It's at the second level. You're saying 2P, right? Because this is the 2S, this is the 2P. This is the 1S. So we start off with the 1S. We have 2S, 2P. So this is just, this 2 refers to all the ones at this level. All of the electrons at this level. So that's what that 2 is for. Do you guys get that?
Yeah. Now I know where I got lost, so it makes more sense now. And then so now we move over to the 3rd level, right?
That's right.
Okay.
Dr. Henry,
Yes, sir.
I just have a question. You know, like on the first one, Y1, S2, right? On the S star here. And then you go over there to the helium, right? It's not going to be 1P1, 1P, you know, 1P, 1P2,
No.
1P1.
No. Helium, because you want to maximize how many electrons you hold before you go to the next energy level. So this is not really the P, this is really an S. It's just because helium's a noble gas, they want to keep it with the noble gases. So they split it up.
Okay.
Okay?
Got it.
So now we're at the 3 level, right?
Yeah.
Yeah.
At the 3 period. Okay?
3S2,
3S2.
3P6, 4S2, 4D4.
Just relax, hold on, slow your roll. This is a learning experience. Okay?
Sorry.
Dang, Nancy.
He's just like, forget you guys, you're taking too long. Come on, let's go. Come on, you're coming.
Everybody's a pro like you.
Okay,
I'm not a
so
pro.
we have 3P6. Okay, so then that gets rid of this one, 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 and that one. So now we go to the next the next period.
Okay.
Okay, so then that's what?
That's gonna be 4S, right?
Yep, and how many?
5? Oh no, 2.
Oh, 2.
Okay,
So
where's my shock collar? I really need shock collars. I think that's gonna be part of your kits next year.
No.
So if you guys don't pass this semester, there are gonna be shock collars involved. Some of you guys may like that a little too much, so don't fail on purpose. Okay, so now this is where it gets funky.
Oh my God,
right?
I gotta quit.
So I'm gonna throw you off completely right now. So right now, this one here is actually the 3D. It starts at the D. And I did this on purpose to get into our next lecture and build us up. So now it starts at 3D. So this is
not
3D.
4D?
No, it's not 4D. Even though this is the 4th energy level, it's D. The D energy level gets shifted back because it's actually higher than the other. And I'm gonna show you that here in a second. So you just stick with me, listen to what I tell you. So if I have a periodic table, the first thing that I would do, since I'm a new student, I would write that this is 3D,
Okay.
right here. And then I know that this is 4D, and then this is 5D, and then down here, 6D.
That is so confusing.
Yep.
So-
Don't worry, it does the same thing for the F, right? So then down here for the F, this here is 4F, right? Even though it's in the 6th energy level, it's 4F. So it shifts down as well too,
Okay.
okay? And then this is the 5F. That's a 5.
Or,
Yes.
five.
Okay.
So, Dr. Henry, you said before that number 71 and 103 are in the D block, so are those also 3D and 4D?
Okay, hold on. Let me shift it back. Right, I'm moving stuff. Yeah. Oh, there we go. Okay, now what were you saying? So in the D block?
Yeah, you said before that like the F that's off to the side, the last two, 71 and 103, were actually part of the D block. So are those 3D and 4D?
No, it's part of, no, it would be 3D because this is 3D up here. All of these are in the 3D. These here. This is 4D. And then this one here, that would be the start. That would be 5D, just this one right here. And then the rest of the Ds are right here. So that's 5D right here.
Oh, okay.
6D, right? So it's still going to number down. So you go 3, 4, 5, 6. But that's only for the D block. And then this guy starts off at 4F. So it's 4F. That would be 5D. Okay. Okay, Jamie. So then here, since this is the 3D, how many do we have in the 3 block? I mean, in the 3. So you just count till you get to that chromium. So that's 1, that's 2, that's 3, that's 4. So then we'd end at, sorry,
Would it be
3D4?
3D4.
3D4. That's right.
Okay. I get it. Oh. So it's
Okay. Okay, so how much is your head hurting right now?
I think my brain's hurting a little more than him.
Nobody's head blew up.
arthritis?
So let's try one more, and then I'm going to send you guys in groups and see what you guys can do.
Wait, is RF 6D?
Is RF?
Yeah. Number.
Oh, no. RF right here? Yes. So that would be, so that's, yes. RF would be 6D, but that's
Okay.
the second electron in 6D. The first one would be right here. That would be also a D. LR, that's going to be 6D as well.
I have a question.
Yes.
So like it's supposed to equal like the amount of
So this one is 5D.
Total amount of electrons. Right? So add it together. We have 2 plus 2, so that's 4, plus 6, that's 10. Plus,
Oh, we're adding the exponent. I don't. Oh, okay.
yes, it's the exponent. That's keep track of the number of electrons.
Oh, okay. I thought it was the
Okay.
number next to the letters. Okay.
Okay. Okay, so let's see. Let's give you one that's going to make your brain blow up, and then I'm going to show you a quick method. Okay. Let's do PR.
PR?
There's enough room to do it. So we'll do PR. PR.
Where is it at? I don't see it.
Yeah, I'm not gonna tell you. You gotta find it.
Okay.
It's part of the test.
Great. Okay.
I need some water. Okay, did you find it?
Yes.
Yes.
What is it? What is it?
59.
59.
Yeah.
Okay, it's right here.
Uh-huh.
Okay, PR. Oh, God. 5F.
We always start from 1, right?
You always start from 1.
Okay, just want to make sure.
Or do we do together? No.
Okay. Let's go. You ready?
Go.
I'm not saying a word. You guys are have to tell me.
No, wait, not yet, not yet. So, you said that that row would now be 5. It would be 5F.
No, it starts off at 4F. I had to shift it down, so let me erase.
So 4F and then the bottom row is 5F, right?
Yep.
Oh,
four.
row.
Yep. 4F right here.
Yeah,
and
4F.
5F.
Yeah.
Yep. Okay, are we ready?
Let me say that we start off with the 1s2, right?
Okay, so we started with 1s2.
Mm-hmm.
1s2.
Okay, who's next?
2s2. 2s.
2s2.
2p6.
Now, Nancy, you got to share.
Okay.
You act like you're an only child.
And then 3s2.
3s2.
And 3p6.
3p6.
You guys so fast.
Okay.
1, 2, 1, 2, 3, 4, 5, 6. Okay.
4s2, right?
Okay, 4s2.
4s2. 4,
3g.
4d. No, 4d. 3d.
3D10,
3d10.
Oh, that's a lot.
4P6,
G 4p.
Go 4x. iPhone 4x.
5S2, 5S2.
Okay, so that gets rid of this.
Oh,
That makes sense. Okay, hold on.
And then
5S2.
What? Okay.
Okay.
4d10.
4D.
5D. 4D. Yeah.
4d10.
4D. And then
5p6.
5p6.
6.
6S2.
And what have you?
6s2.
That's
And then it's gonna
Would it be 4F3?
5.
And then it would be 4f3. That is correct.
So do we skip the 5d6? 5d6?
Nope, you go to F first, and then you go to 5D. So it's 4F, then 5D.
Oh.
I get that now.
But we never get there because we stopped at 4F3.
1, 2, 3.
Okay. Okay.
Ah, I get it now.
You get it?
Yeah, I get it.
Okay, so you see how much we have to write for that one question? For that, you guys see how much we have to write for that one question?
Yeah.
Okay, so the way that you trim it down is by using the noble gas that you passed. So what was the noble gas the nearest noble gas that we passed?
Radon.
So then you put that
No.
in brackets.
Xenon.
Are you sure it's radon? That we
No, it's xenon.
Radon and xenon.
Xenon. I can write an E. And then you put what's left after, so that'd be 6s2 and
4F3.
4F3. So what you're saying is that we've already counted all the ones by just putting that noble gas, and then anything that's left over, which is this guy and these guys. Right there. That's
So
it.
I'm a little confused. So why do we skip 5D and 6D?
because 5D is right here, right?
Oh, okay.
Okay, so let me show you what the periodic table really looks like.